Hello students and welcome to the 44th lecture on particle physics. And in the 43rd lecture, we were talking about Lepton-quark-symmetry. We had started discussing about the leptonic interaction. And what I had told you that we have three generations of leptons, electron family, muon family and tauon family. And these are the lepton numbers associated with them: electron lepton number, muon lepton number and tauon lepton number. Then we have quarks, and we have here also we have three generation of quarks: up down, charm strange and top bottom. And then the important point is that when we are talking about the interaction of electron with muon, for example, or electron with proton, for example, then the scattering cross section, for example, if I am talking about electron proton scattering, I am talking about electron muon scattering, I am talking about pion proton scattering giving rise to say pi 0n. Here this is electron and muon in the final state. Here we have say electron and proton in the final state, or you can say that electron plus neutron plus pi plus in the final state. And similarly here also you can have even elastic scattering, pi minus p in the initial state and pi minus p in the final state. These are the electromagnetic interaction process. Electron is interacting with a proton, but this interaction may also take place via Z0 exchange, which is a neutral current interaction mediated by a weak boson, and that weak boson is a Z0 boson. Therefore, my point is that if we are considering electron and we are saying that electron is interacting with a muon, or electron muon scattering is taking place, this will happen only when there will be a mediating quanta. In the electron muon scattering, the mediating quanta will be a photon. If we are talking about electromagnetic interaction, if we are talking about weak interaction, then this will be a Z0 boson. How do we understand it? What I had told you on the last turn, that actually an electron interacts with a photon field. And here we have the coupling, which will be electromagnetic coupling in the case of photon, and this will contain the strength of the interaction and this will contain the nature of interaction. Therefore, when we are talking about coupling, this coupling in the case of photon, this will be a vector coupling, because photon is a vector particle, a spin 1 parity odd particle. Photon, if we recall from the properties, this is a spin 1 parity odd particle. This is a vector particle. Okay. Therefore, this interaction is a vector in nature. And then we have the strength of the interaction. Now, the same scenario, instead of a photon, this can happen when an electron is interacting with a Z field, where the particle is Z0. Now, in this case, again, we will talk about the strength of the interaction and we will talk about the nature of the interaction. Now, the strength of the interaction will be different than the strength of the interaction in the case of electromagnetic coupling. And typical coupling that we talk about, if we say that for strong interaction the strength of the coupling is say 1, then in the case of electromagnetic interaction the strength of the coupling will be 10 power minus 2, and in the case of weak interaction the strength of the coupling will be of the order of 10 power minus 6. Therefore, one thing that will come into play when we will have a gluon exchange when we will have a photon exchange, when we will have a W or Z0 exchange. This is, we are talking about the strength of the coupling, which is of the order of 10 power minus 6 at the, that will translate into the cross section. The electromagnetic interaction strength, that will a coupling strength, that is of the order of say 10 power minus 2, and the strong interaction coupling strength 1. And if we talk about the cross section, then if we are talking about these guys, pi minus p going to pi 0 n or pi minus p going to pi minus p, the cross sections are of the order of 10 power minus 26 centimeter square. While if we are talking, so therefore this will be for pi n scattering. If we are talking about a photon scattering on a nucleon, and we have some particle, a nucleon and a pion in the final state, this can be a pi 0, pi plus or pi minus. We have to look at the charge of the particles. We know we have to conserve charge. Then this will be of the order of 10 power minus 30 centimeter square. And this guy, in the case of weak interaction process, if we are talking about say nu mu scattering on the neutron target, and we have a muon and a proton in the final state, then this cross section will be of the order of 10 power minus 38, 10 power minus 40 centimeter square. Therefore, if you notice why the cross section is coming small, this is because of two reasons. One is the nature of the coupling involved, the strength of the coupling, and the second that we talked about on the last turn, that it was the propagator, because ultimately what we are talking about, that okay, electron is interacting with a photon field. Similarly, this muon will also interact with the photon field. But if we are talking about electron muon scattering, electron muon in the initial state and electron muon in the final state, then the Feynman diagram, which is a pictorial representation for a scattering process, is such that an electron emits a virtual photon, because this photon is not on mass shell. On mass shell means if say this has got 4 momenta k, this has got 4 momenta k prime, this has got 4 momenta p, this has got 4 momenta p prime, then the 4 momentum transfer is k minus k prime or p prime minus p, and q square, the 4 momentum transfer square, which is for on mass shell particle is mass square, for off mass shell particle is not equal to m square. While the real photons are always transverse in nature, the virtual photon has both the longitudinal component as well as the transverse component. Therefore, the important point is, when we write the expression for cross section, which is equal to the amplitude square from the Fermi's golden rule that you know, then the amplitude, this part, this contains coupling strength besides other quantity, and this contains the propagator and many other quantities. Now, if we are talking about electromagnetic interaction, this coupling strength will be different and the propagator will be different. While if we talk about weak interaction, there will be new coupling strength, say let us call it by the C2, and here the photons are massless, but the W bosons are massive or Z0 bosons are massive. There you have in the Feynman rules you have propagator that is proportional to 1 over mw square, and this mw is around 80 JeV and mz is around 91 JeV. Therefore, these are very massive objects, or it is like an elephant sitting in the denominator, which will make this guy to be relatively much smaller in magnitude, such that the cross section for electromagnetic interaction will be of the order of 10 power minus 30 centimeter square, while for the Z0 exchange, in this case, this is in principle taking place via photon exchange as well as Z0 exchange. For Z0, the interaction cross section is 10 power minus 30 centimeter square, while in the weak interaction cross section mediated by a Z0 exchange is of the order of 10 power minus 40 centimeter square. Now, if we talk about neutrino electron scattering, either nu E is interacting with electron or nu mu is interacting with an electron, then you will have only W exchange or Z exchange, and then that means you will have weak coupling strength as well as the heavy propagator in the denominator, such that in these cases the cross sections are always of the order of 10 power minus 40 centimeter square. Therefore, the important point is, the important thing to understand that if a neutrino is coming and it is emitting a W plus boson such that it gets converted into an electron, then for a process like neutrino electron scattering, say instead of this, if I talk about neutrino electron scattering, then what is happening? A neutrino is emitting a W boson and that gets absorbed by an electron, incoming electron. And since it has emitted a W plus boson at the vertex to conserve charge, it has to get converted into electron, keeping in mind that at vertex we must have the lepton number conservation, electron lepton number, muon lepton number, tauon lepton number, again independently. And then this electron is absorbing that W plus and it is becoming a nu E. Therefore, you can see that nu E electron we are talking about and nu E therefore, this is representing a process or scattering where we have neutrino and electron in the initial state and neutrino and electron in the final state. This is what we call it by the name neutrino electron scattering. Therefore, the important point, now here we have the coupling strength, and this coupling strength, let us say we are representing it by GW. This is what we were discussing on the last turn, that the coupling strength between nu E and E minus, coupling strength between nu mu and mu minus, they will be of the same strength. This is what we call it as universal lepton symmetry, or in general lepton universal symmetry. What is that? This states that if you have a nu E which is emitting a W plus and it is getting converted into electron, or you have a nu mu that is emitting a W plus and it is getting converted into nu mu, this strength here and here, the coupling strength, if I am representing here by GW, then here also I have to represent it by GW. Or if I have a nu tau and a tau minus W plus, this is represented by GW. That means if we are talking about the neutrino electron scattering, nu mu muon scattering, nu tau tauon scattering, if I, instead of that, if I draw the three different Feynman diagrams where we have W exchange. Let me just draw it and then we will start discussing about it. Say we are talking about a nu E emitting an W plus, getting converted into electron. This nu E is getting absorbed by electron, and it is, when it is electron is absorbing W plus, it is getting converted into nu E, or nu mu, it is emitting a W plus and getting converted into mu minus, and this W plus gets absorbed by mu minus and it gets converted into nu mu, or a nu tau emits a W plus, gets converted into tau minus, and this tau minus is absorbed by W plus is absorbed by tau minus, and this tau minus gets converted into nu tau. What this universal lepton symmetry tells you, that the coupling strength here, 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 or here, here, and here, all 6 places, the coupling strength will be represented by GW. And the propagator, since everywhere is W, the propagator will be 1 upon mW square. It will be proportional to 1 over mW square. Therefore, the propagator is proportional to 1 over mW square, and the coupling strength here will be GW, here will be GW, and all 6 places it will be GW. This is known as lepton universal symmetry. Now, with this idea in mind, when we go to quarks, and since quarks are also point spin half particles, therefore the lepton-quark symmetry tells us that the coupling strength initially that was assumed to be the GW for neutrino electron vortex or nu mu muon vortex should be the same as for UD vortex. And this is what is very important topic which we should try to understand. Therefore, what we are talking about, the lepton universality, is a fundamental principle in particle physics that states that the interactions of different types of leptons, electron, muon, and later the third generation family of leptons, that is tauon, with the nuclear force should be identical apart from difference due to their masses. Only the difference will be electron mass is different from muon mass, and that will be difference from if we talk about tauon mass. Therefore, the important point is nu is emitting a W plus or E minus is emitting a W minus and getting converted into nu E, or nu mu is emitting a W plus and getting converted to mu minus, and so on. This vortex, the strength of the interaction, the strength with which the coupling is taking place with a W boson will be the same in all the cases. Later, here we are talking about only 2 generations. But when the third generation of leptons came into the picture, the same analogy was applied in that case, and it was found to be true. Therefore, not only that, this is not only true for neutrino and electron, this has been found to be also true for E plus and nu E bar, another weak doublet. Therefore, nu E bar is emitting a W minus. See, on the last one we have discuss this. A particle coming towards the vortex is represented by an incoming arrow. An anti-particle coming towards the vortex is represented by a downward arrow. A particle which is going out is represented by an arrow outward, and anti-particle going out is represented by an arrow inward from the vortex. Now, this will be true for E plus as well as nu E bar. This will be true for E minus, nu E, nu mu, mu minus, whatever particle that you talk about. If that is an outgoing particle, the arrow will be outward. When it is from the vortex, if anti-particles are going out, then whatever you talk about, anti-proton, anti-neutron, this will be the downward arrow from the vortex. Therefore, these are the Feynman convention of when writing down the transition matrix element. Therefore, the important point is that whether we are talking about this guy or this guy, the interaction strength, the nature of the interaction, or whether it is emitting a W plus or a W minus, this will all the time will be GW. Or from vacuum, we have E minus, nu E bar and W plus, or E positron, neutrino and W minus, giving rise to we have a vacuum in the final state. The vortex will be represented by strength of the vortex by GW. Now, the other important point is we cannot, in the Feynman rules, we cannot have a nu mu coming which is giving rise to W plus and getting converted into an electron, because independently at the vortex we have to conserve lepton number individually for the first generation, for the second generation, and for the third generation. Then if we have a baryon, then we have to also conserve the baryon number. That means if a quark is coming to the vortex, from there an anti-quark cannot go out. because baryon number of quark is 1 by 3, for anti-quark is minus 1 by 3. That also is a subtle concept which we should keep in mind while drawing Feynman diagrams. Therefore, it has been tested extensively in experiments, particularly at the Large Hadron Collider at CERN, measured various processes involving leptons to verify that they behave in accordance with lepton universality. That means it has been conserved or it has been tested to very high accuracy, and this is not allowed because of the lepton number conservation. Now let us come to the Lepton-quark symmetry. What is Lepton-quark symmetry? Now, in the standard model of particle physics, leptons and quarks are both classified as fermions. Both are point particles. Point particles means they are structureless particles. They are spin half particles. Therefore, they are structureless particles. They are spin half particles, and they are member of the standard model of particle physics. They are member of the basic building blocks of the universe. Okay. Now, leptons and quarks, since they are both classified as fermions, that means they obey Pauli's exclusion principle, and all the rules of quantum mechanics are equally applied to them, except with the one fact that we have to keep in mind, that leptons participate in weak interaction and electromagnetic interaction processes, while quarks participate in all the three interaction processes which we considered in the standard model of particle physics, with strong interaction, electromagnetic interaction, and weak interaction processes. However, that means these electrons, muons, and tauons, they do not feel a strong nuclear force, while quarks, they make protons, neutrons, and other hadrons. They are participating in all the three interaction processes, like strong, electromagnetic, as well as weak. Now let us come back to the fundamental picture, because initially we had 4 leptons, nu e, e minus, and nu mu, mu minus. Tau-on lepton was discovered later in 60s, and then it was thought that if tau exists, then nu tau should also exist, and nu tau is the discovery of 21st century almost. So therefore, the important point is that we have in early 1960s, we had 4 leptons, nu e, e minus, and nu mu, mu minus, which we divided into 2 generations, electron type neutrino and electron in the weak isotopic spin doublet, and muon type neutrino and muon in another weak isotopic spin doublet. Similarly, we had the doublets for the antiparticles, while at that point, if you remember, late 1950s, we had, or early 60s, we had up and down quark only to describe proton and neutron, and these were the first generation quarks, and then strange quark was placed in a singlet that was all alone. We had up and down quark in a doublet, isotopic spin doublet, while like proton and neutron in the isotopic spin doublet, while strange quark was all alone, that is, it was a member of singlet. That we in terminology, isospin terminology, we call it by the name isosinglet. So therefore, the 4 leptons were experimentally observed in the laboratory as isolated particles when the quarks reside inside the proton or neutron, or in general we say that it's a hadron. Therefore, the vortex that we talked about for the neutrino electron scattering or electron interacting with a neutrino via W plus exchange or W minus exchange, similarly, what was thought that since U and D quarks are also fermions. They are spin half particles. Therefore, they will have similar W interaction as that of electron and neutrino. Now, mind it, what I am telling you, that like nu E minus, we have the similar weak interaction for U and D isodoublet, and that means the coupling strength for U with W will be the same as the coupling strength for nu with W, and that is what you can see here. I am showing it by nu in emitting a W plus getting converted an electron. The vortex is represented by GW. Now, since if we assume that lepton-quark symmetry holds good, then instead of nu E, what I am telling you, that we have a U quark, and this U quark is emitting a W plus, and it is getting converted into a D quark. We are conserving baryon number because the total baryon number arriving at this junction is 1 by 3. Total baryon number leaving from this junction is 1 by 3. And the total charge arriving at this junction is 2 by 3 from U. And how much is leaving? Plus 1 from D and plus 1 from W plus and minus 1 by 3 from D. Therefore, we are conserving charge. We are conserving baryon number. Similarly, here we can say that a D quark is emitting a W minus and it is getting converted into a U quark. Therefore, minus 1 by 3 here, minus 1 charge is getting emitted and this charge is 2 by 3. You can see that baryon number we are conserving at the vertex, we are conserving charge. So therefore, what is this lepton-quark symmetry all about? This tells us that in the weak interaction, the coupling strength for the first generation leptons will be the same as the coupling strength for the first generation of quarks. This was first thought about, and therefore what we are saying that this GUD must be equal to GW. This coupling strength U with D must be equal to with GW. Now, the important point is, since we cannot have the isolated quarks, the naked quarks, independent quarks, those exist in nature. We know that quarks exist in bound states. Therefore, then we have to go back to the experiments. For example, if we talk about pion decay or we talk about a pi minus decay, then we know that a pi plus decays to mu plus plus nu mu, or a pi minus decays to mu minus and nu mu bar. And that means a pi plus is made up of U D bar quark, and this is giving rise to a W plus, and that W plus is giving us a mu plus and a nu mu. Again, see this inward arrow going for anti-particle from the vertex means this is an outgoing anti-particle and this is an outgoing particle. Therefore, in both the cases, both the particles are outgoing. In the Feynman rules, the outgoing anti-particle is represented by an arrow which points towards the vortex, while an outgoing particle is represented by an arrow which is moving away from the vortex, as has been shown. Therefore, the important catch is that here you see a W is interacting with a muon and a neutrino. Therefore, this vortex should be GW, while this is the quark vortex, which this is GUD. Similarly, here this is GUD and this vortex is GW. Now, what this lepton-quark symmetry tells you, that the strength of GW should be the same as strength of GUD. That the coupling of UD with W quark or anti-U, anti-D with the W quark will be the same as the coupling of the leptons. But where is the crisis? The crisis is that in the case of leptons, we have individual lepton number conservation. for the first generation leptons, for the second generation leptons, and for the third generation leptons. But in the case of quarks, all the 6 quarks that we talk about, they all have baryon number 1 by 3. Now at that point, U and D were placed in a doublet, while S was placed in a singlet. Now what people observed, that a kaon also, which is made up of U bar S quark and K plus is made up of US bar quark, because remember, this has a strangeness +1 and this has a strangeness -1, and strange quark is assigned strangeness quantum number as -1. Therefore, if it is a strange quark for K minus, the strangeness is -1, while anti-strange, the strangeness quantum number is +1. Now you see, here we are talking about a mixing of U with S quark. And this has been experimentally observed, that a K plus decays to mu plus nu mu, or a K minus decays to mu minus nu mu bar. That means, unlike in the case of first generation leptons or second generation leptons, here you have a mixing of U with S. And that means this picture of having the same coupling strength may not be true when we are discussing about Lepton-quark-symmetry. Similarly, not only in the case of kaon decay, we know that a neutron decays to proton plus electron plus antineutrino, where neutron is made up of UDD quark, a proton is made up of UUD quark. How we are understanding this decay? We say that a D quark is changing to U quark, and that means a -1 by 3 charge is getting converted into 2 by 3 charge, and this can only happen when it will emit a W minus. Therefore, in the quark picture, if you look at it, this is a neutron. Therefore, this is UDD, and this is getting converted into proton, which is UUD. Therefore, I am writing this D. This D can become U only when it emits a W minus, and that W minus is giving us E minus and nu E bar. Therefore, a neutron decay has been observed, or inside the nucleus, a proton decay inside the nucleus, a beta plus decay has been observed, as proton is getting converted into a neutron plus E plus nu E, and this proton is UUD, it is getting converted into UDD. That means here a U is getting converted into D, and this can happen when it will emit a W plus boson. Therefore, if I am writing like this diagram, this is emitting a W plus, and then this give rise to a E plus and a nu E, and this U is getting converted into D, UDD. This is UD. A proton is getting converted into a neutron by emitting a W plus, and that W plus is giving rise to E plus and nu E. Therefore, everything is fine. This is a conversion of U to D and D to U, and therefore, if we talk about the coupling of U with D, that would be the same as the coupling of nu E with electron. But what has been found, that not only a neutron gets converted into a proton, we have also lambda decay, where a lambda decays to proton plus electron plus antineutrino, or a sigma minus decay, where a sigma minus decays into neutron plus electron plus antineutrino. Therefore, like we have K plus and K minus decay, here we have lambda decaying into non-strange particles like proton. Sigma is also decaying into non-strange particles like neutron, and that means what is actually happening? A S quark is getting converted into a U quark at both the cases. If you look at it, look at them carefully. Therefore, S is getting converted into U by emitting a W minus. S is getting converted into U by emitting a W minus, and that W minus is giving rise to electron and antineutrino. Therefore, the picture is not exact if we compare with the lepton sector. Here, mixing of U with X is taking place, as well as there is already mixing with U and with D, as we saw that neutron is decaying into proton, proton is decaying into neutron inside the nucleus, and then a pion decay is taking place, pi minus decay is taking place, pi plus decay is taking place. But at the same time, there are strange particles decay where K plus, K minus, lambda, sigma minus, and that involves conversion of either S to U or U to S. And there came the picture of Cabby-Bow hypothesis, which we will discuss in the next class. Let's just stop here. Have a good day. Thank you.